conjugate theorem, right? And some of you may have picked up on this, some of you may remember it from Algebra 2, but this is the official intro to it, okay? So we've got a bunch of theorems in Chapter 2 with polynomials. Complex conjugate theorem is used heavily, I think. But what it says is if you have a complex zero or root, a plus bi, right, then its conjugate, a minus bi, must also be a root or a zero. Can. That's okay. Yeah, thank you. Mr. Patchers. Right, so again, one of the reasons we study conjugates is related to this. So yeah, if a plus bi is a root or a zero, then a minus bi is a root or a zero. They come in pairs no matter what. You absolutely cannot have one without the other one. They come together, okay? And we'll try to explain some of those reasons of like why that's going to happen. But for now, just know that if you have one real, or if you have one complex root or zero, then its conjugate is also a root or zero. So, for example, if 3 minus 4i is one root, then 3 plus 4i is the corresponding root that pairs with it, no matter what, right? Seems pretty basic, right? So if negative 5 plus 7i is a root, then negative 5 minus 7i is the other root. So if I tell you one of the roots, it is your responsibility to automatically know that that is another root, no matter what, okay? It goes the same with these irrational roots too, okay? So these are not complex. A plus square root b. It's a radical that does not simplify, right? So you can think of it as 3 plus square root 2. They follow the same pattern, right? So if you have a root that deals with a radical that does not simplify any further, meaning you have a radical in your answer, conjugate to that radical is, or the conjugate to that root or zero is also a root or zero. So a plus root b, then a minus root b, right? So 5 minus root 3 is a root or zero, then 5 plus root 3 is the other root or zero, no matter what. So again, if I give you one, you're responsible for saying that's the other one, and eventually we're going to use roots to write polynomial equations. So we started with polynomial equations and we solved them to find roots or zeros. Now we'll give you roots or zeros and you're going to work backwards to produce the equation. So if I give you one, you need to know that this is also a root as well. Okay? So it's shortened into the conjugate theorem. Complex conjugate is specific to complex values, but it's the same idea, right? So 1 plus root 2i, then 1 minus square root 2i. 3 halves minus root 5, then 3 halves plus square root 5. You should remember this from Algebra 2, yeah? Okay. All right, so this is where it shifts gears a little bit right now. And